Hi, I'm Peter Norvig, and in this second video on AI, I'll show how the era of big data changed everything. Now, for the first 3/4 of the 20th century, industrial workers powered America and the world. A combination of muscle, brains, and machine power allowed society to grow at an unprecedented pace. Now, this slide shows how a mathematical equation for torque allowed for the development of machinery that enabled mechanical work that went far beyond what a human could do on their own. Nobel laureate Eugene Wigner noted how remarkable it was that mathematics was such a good fit for these advances. We're still not sure if that's because the world is made that way or because we made mathematics to match the world. But in any case, simple equations allowed us to do so much. Then, for the last quarter of the 20th century, manual laborers were joined by information workers, such as programmers. Instead of one-line formulas, we have million-line programs. Software is more malleable than steel, but it got too complex. Mass-producing the second and subsequent copy of software is trivial, but designing the first copy is tough. Now, in this first video, we saw how traditional software was ill-equipped to tackle problems involved in an uncertain world. We saw that artificial intelligence expert systems were a way to tackle some of these problems. But expert systems had their limits. The real world is messy, and it's hard to specify all the exceptions to rules. The schematic chart at the bottom of this slide is meant to say that every time you add a new rule to an expert system, it handles more cases correctly. That's the green line. The more rules, the more cases you cover. But it's also the case that two rules might inadvertently interact badly and produce errors. So eventually, the bad interactions, the red line, the red curve, outweigh the good, and the system collapses. We discovered that we need a new way forward. Now, that way was evident from the very start of AI. Alan Turing, the founder of the field, wrote in 1947 that what we need is a machine that can learn from experience. And he even warned that such a machine might outstrip ourselves. We call this approach machine learning. So let's contrast the two approaches. To build a chess-playing program, the expert system approach would encode rules of thumb that expert chess players use, describing the value of pieces and positions and the kind of tactics to try. With a machine learning approach, you don't need any of that. You just explain the rules, let the program start playing games against itself, and when it makes a mistake, change itself. Even if the changes are random, eventually it will learn to make more good moves and fewer bad ones, until it plays better than any human. So to recap, AI is part of software engineering, machine learning is one approach to AI, and deep learning, which we will get into in the third video, is a kind of machine learning. Now, in the machine learning approach, we have to be comfortable with giving up control. As General Patton said, explain what you want done, not how to do it. You may be surprised with the creative ways to get things done. And as the famous philosopher Yogi Berra said, you can observe a lot just by watching. In statistics, we observe some data, and that allows us to make predictions in the form of a curve that fits the data. All of machine learning is like drawing that curve, except that the data and the curve are much more complex. Now, machine learning existed since 1947, but it has come to the forefront in the last 2 decades because of the vast amount of data now available on the internet and the possibility of creating new data by interacting with users. With machine learning, you're less likely to deceive yourself. You won't be following rules of thumb that are wrong. However, it's still possible that the data may contain biases, and that can lead systems astray. Biases come from many sources. People have prejudices, and the data picks up those prejudices. Garbage in, garbage out. And even when there are no biases, the lack of data can lead to poor results. There's a lot of text available in English, so English language models are really good. But for languages with fewer speakers, like say Lithuanian, there's less data, and thus the models are not as good. So maybe that's a bias against Lithuanians. It may be that we collect the wrong data or incomplete data. People in one country may not be aware of how other countries work and make bad assumptions. And finally, remember that all data is just a proxy for reality. For example, suppose we want to know where crimes are being committed so we can try to do better policing. But we don't have that data. All we have is arrest data. And that arrest data depends both on whether crimes are committed and also on the policing used to observe it. Now here's an obligatory chart to show that there's lots of data out there. For every human, there is the equivalent of billions of pages of data, although some of that is duplications. So let's consider an application of the machine learning approach to the problem of translation using data. Here, it's a translation from English to German, and programs today do pretty good. How will we build a program like that? Well, we can go out in the world and collect pairs of English-German translations. Here's a couple of them that I found in my hotel room in Berlin. And now we know sentence-for-sentence translations. And through a process that I won't explain the details of here, we can break that down to phrase-for-phrase and word-for-word translations. We end up with a database like this that says how many times each of the English phrases was translated into which German phrase. Now here's the only math equation I will show. It's the fundamental equation for statistical machine translation. It says that the best English translation, E, of a foreign language passage, F, is the one that maximizes the probability of E, that is, the probability that E is a good grammatical sentence of English, times the probability that F is a good translation of E. Now the first part, P of E, we estimate by looking at all the English texts we have and counting up how often words occur. And the second part, P of F given E, we estimate from the paired translation database. This equation is a theorem of mathematics known as Bayes' law. But now, a curious thing happens. If we solve for this equation, we get pretty good translations. But if we change the equation to raise P of E to the 1.5 power, we get better translations. Does that mean that Bayes' law, a 250-year-old theorem, is wrong? No. What it means is that there's a difference between the true probabilities and the ones that we estimate or derive from the data. Since we have more data about pure English text than we have about English foreign language translation pairs, that 1.5 says to put more trust in the data source that we have more of. Fred Jelinek allegedly said that anytime a linguist leaves his research group, the recognition rates go up. Fred worked to change the fields of speech recognition and translation from using expert systems to using machine learning, and he's very successful at it. What he's saying here is that machine learning works better than the intuition of linguists. Now let's look at another machine learning application, image understanding. Alan Turing talked about the way a child lives in the world and learns. We wanted to approximate that experience to some degree, so we exposed a computer to YouTube videos, a microcosm that reflects some of what happens in the real world. Now, in 2012, we couldn't match everything that a child sees, but we did hand 10 million video frame images to a network of 16,000 computers and had it estimate the best fit to those images, just like how the statistician draws a curve, except that a parabolic curve, say, has only 3 parameters, the ABC and y equals ax squared plus bx plus c, and our model had 1 billion parameters. And here's 2 examples of the types of patterns it detected and putting them together. This is YouTube, so of course there's going to be cats, and there's also human faces. And here we asked the system to show the best example, the average in a sense, of these 2 patterns. And so here it's being generative AI and it's generating a cat and a face. This was 2012, so you can see how far we've come since then. What our computer has done is observe the world, and with no help, just what it sees on its own, it has invented the concept of cat and of face, among many, many other concepts. Now, around 2012, experiments like this started to excite researchers and revolutionize the field. A big part of that was putting together better data sets, such as the ImageNet collection of images with labels. In the work I just showed, the system could cluster together the cat pictures, but it didn't know that they were called cat. With ImageNet, that loop is closed. Work like this and many other examples showed that modern machine learning approaches with access to lots of data are capable of recognizing patterns in the data, which reflect realities of the world. In most cases, the machine learning approach is better than the handcrafted expert system approach. We're very good at using data to optimize some criteria. Make the chess move that most likely results in a win, for example. And for chess, that's easy because we know winning's good, losing's bad. But in more complex areas, it's often the case that figuring out what we want to optimize is the hard part. We'll get into that in the third video. Thank you for watching.